Okay, so hello everyone. Uh, I am Saurabh Bhadra and welcome to this nuclear astrophysics TS course. I am the tutorial course and today is the first tutorial. So this class will be on Tuesday from 6 to 8 p.m. But due to some personal reason for this week only, I am taking it on Saturday. From the next week, it will be on the Tuesday 6 to 8 p.m. Okay, so currently I am a PMRF PhD student in Indian Institute of Science, and I am mainly working in astronomy and astrophysics. Okay, so I will take the tutorial on the basis of the given assignments. Okay, so today I will mainly focus on the assignment 1, and I will not only solve the questions one by one, but will try to give you an overview of the background, the theoretical background of those questions. Otherwise it will be like remembering things and not understanding the underlying physics or other things. So I will try to give you some idea about the underlying physics also. You don't have to note it or write down in your notes. Just follow what I am saying and try to understand. Let me check. Yeah, sound is okay. Okay, fine. So first I will focus on the HR diagram, because you can see in the assignment there are some questions from the HR diagram. But before jumping to the questions directly, I will give you some theoretical background. Okay, so that you can understand that HR diagram in a good way. Okay, so this I will start from the radiation from a stars. So stars actually radiate like a black body. So this figure you can see, it is a the x-axis is the wavelength and the y-axis is the flux. So what is flux? I will come into that. So now you can think it as a energy. So the y-axis is telling you how much energy the star is, the energy output of the star at each wavelength. So you can see that there are various different temperatures. So 3500, 4200 and different various temperatures have been shown in the plot. And this curve, this that curve which is not continuous, which have this type of structure, this is the spectra of a particular star which has temperature of 3500 degree, this one. And this continuous curve, this continuous is actually the spectra of a black body at that same temperature, or for the first curve it is 3500. So here you can compare it, the smooth black body curve with the discrete not discrete, the random stellar spectra, and you can see that it closely follows a spectra of a black body. So we can treat stars as black body radiation, stellar radiation as the black body radiation. So this is a marvelous result or findings, so that we can develop the radiation theory of stars based on the black body spectrum, which we have studied already in our BSc course. Okay. Okay, so as you know that the energy density of a black body radiation, you knew, goes as this I will not prove, I think everyone knows this, that 8 pi nu square by c cube h nu by e to the power h nu by kt minus 1, and the unit is arc per semicube per hertz. That means it is the energy per volume per unit frequency. That's why it is written as u nu. Okay, now this is the energy density. We cannot measure the energy density from a star when we are measuring by sitting at the earth or from the space detectors. So we measure generally the flux of the star. So from the energy density, how we can calculate the flux, that I will come step by step. It will not take much time. Okay, so this is the flux, this is the energy density, you know, that is coming from the black body. Now this from this energy density we can calculate the intensity of the black body or the star, whatever you can say. So the intensity is actually calculated by this d u nu by d omega. So here du nu by d omega is the differentiation of this energy density with respect to solid angle. Now solid angle may be a new concept for you. So this, consider this image. So you know that if we are in 2D, suppose this is an arc, okay, suppose this is an arc of a circle and this is the center. So for 2D case, this arc will create an angle which we call a general angle. But when you are considering a 3D 3 dimension, then the concept of solid angle comes. So solid angles is actually the surface. So it is a sphere, this is a sphere, and the surface of the sphere, I mean this particular segment or this particular segment, this surface I mean creates how much angle at the center. So you can think it as a 3D. So you have a surface like this is your surface and that is the center. So what is the angle this 3D surface is making at the center? That is called the solid angle. Okay, so for 3D case, the solid angle is utmost important. We cannot consider only the 2D angle, which is theta. So that's why this solid angle comes into the picture, that tells you that how much energy is going through the surface of a sphere. So if you calculate, I mean you just try to get the idea, not the theoretical calculation is not that much important for this course, but the idea is important. So from here you can calculate that and if your radiation is homogeneous, that means this is your star and suppose this is a sphere around the star. I mean it is a space, it is a spatial volume, and the radiation is coming all over the is going through all over the surface. That is the homogeneous radiation we are considering it. And for homogeneous radiation, the omega, that is the solid angle, is 4 pi, because you know a sphere creates a 4 pi solid angle at the center of the sphere. So that's why for homogeneous case it is 4 pi. Now if we consider the homogeneous case, then see this u nu and d omega is 4 pi. So just put this u nu, which I have written here, and multiplied with c and divided by 4 pi, you will get this result, which is called the intensity of the star. So intensity we have calculated, and you can see that here the unit was arc per semi-cube per hertz. We have multiplied by a velocity, that's why length, it has been multiplied with the length, that's why it is centimeter to the power -2, and we have divided by the solid angle, that's why this x dash steradian inverse is coming. So the main difference between intensity and the energy density is the intensity is the energy density times velocity of the radiation, which is the light speed, times the solid angle. So this is I nu, which is very much important, and we can measure I nu in the astronomical using the astronomical instruments. But so that's why I nu is the important thing. Now we will calculate the flux, which is the most important thing, and which has been plotted in the y-axis of this plot also. That is the flux. Whenever we plot we show a spectra, we measure the flux as a function of either wavelength or the frequency, whatever you can do. So so the flux can be calculated by this. So this was your I nu, this was your I nu, that means intensity. And intensity, as I show you, that it is going in every direction, so it is a vector. So this is the intensity vector, and suppose it is making an angle theta with the surface through which it is going, and so this is the angle theta. So you can calculate the flux through that surface by doing the integration over the solid angle, I mean the total angle subtended by the surface. So the integration is over the solid angle d omega. Now you so if you do it, you can see that your result is c by 4 u omega. So why I am pointing this, because you have already calculated u omega from here, and I omega is in your hand, and the flux is c by 4 times u omega. So the just multiply that u omega, not u nu. So if I have said omega, so pardon me, it is u nu, that is my mistake. So if you put the u nu and multiply it by c by 4, you will get this result. This is the flux, okay, and the unit is arc per second per semi square per hertz, okay. So this was the flux. The now flux means, okay, so this f nu means you have a star and you are considering a sphere around the star, radiation is going through that surface, okay, and this f nu is the flux which is going through that surface, okay. That's why it is per unit surface. Now if you want to calculate the luminosity of the star, then the flux per surface, that is already we have, times the total surface area. I mean, we have to multiply it by this area to get the total flux which is coming through the star, okay. That we measure. We can also measure the I nu, but generally we measure the L, that is flux, which is the important thing. So I nu, so F nu is the flux per unit surface. Now you have multiplied that F nu with the 4 pi r square. 4 pi r square is the area of that surface, and you will get the L, luminosity. It is measured generally, okay. So and you have seen that HR diagram. The plot is luminosity and the temperature. That's why I am coming to the luminosity from the energy density of the star. So this is how you calculate luminosity. Now one thing you should consider here, every quantity has subscript nu. That means we are measuring this luminosity at a small frequency band, that is nu to nu plus d nu, okay. Now when we measure, a detector measures the flux, it can measure the bolometric luminosity. Bolometric luminosity is actually the total luminosity in each wavelength, okay. So generally that is that means you have to integrate the L nu over the d nu. So this is actually, just a second, hello. Yeah, so so this L is important, and we will focus this L, which is the bolometric luminosity. That means L nu integrated over d nu, okay. So fine, so that is that I have done. Now we will calculate. So L, as I told you, L nu d nu, right, and this L nu written here. So if I write here f nu 4 pi r star square d nu. Now that 4 pi r star square is the volume of the sphere, so it will come out of the integral, and it will be 4 pi r star square f nu d nu. So this f nu d nu is the f nu, this flux per unit flux per unit area. So it can be written as, so this f nu d nu can be written as capital F only, similar way. That is, I have integrated the frequency dependent flux over the frequency range, that is the F, okay. So 4 pi r star square times F. So this is square, okay. Now if we can calculate the F, we can create a relation between L and the parameter, other parameters. Why I am talking this? Because you can see this f nu is c by 4 mu nu. So we have already find c by 4 u nu. Now we need f, that means f nu d nu c by 4 u nu d nu, right. So this is your f, this is c by 4, and u nu d nu we will write as u. That is the energy density per frequency, which has been integrated over the frequency range. I mean, everything is same, like this is identical. I is equals to I nu d nu, f is equals to f nu d nu. So whenever you can find a frequency dependency, you can integrate it over the frequency range, and you will get the bolometric value, that is the frequency integrated value. Okay, so this u is important, and this u can be calculated from the first thing, this thing. So if you integrate this expression 8 pi nu square by c cube h nu by e to the power h nu by kt minus 1 over d nu, I will not do the integration, you will get the result as a t to the power 4. So it will go as temperature to the power 4. A is a constant. Okay, A is a constant. So you have calculated that F is equals to C by 4 A t to the power 4. Now C by 4 by A, as C is the light velocity, it is also a constant, and you can write it sigma t to the power 4. Okay. So the F, which is the integrated flux all over the energy range, is sigma t to the power 4, and just put this value in this expression and you will get 4 pi r star square sigma t to the power 4, which is very important for the HR diagram. So I will write it here, 4 pi r star square sigma t to the power 4. Okay. So this tells you the relation between the luminosity L and the temperature of the star, which goes as t to the power 4, and there is also another parameter, the radius of the star, r star. Okay. Now remembering this, L equals to 4 pi r square sigma t to the power 4, which is the luminosity, we will go to the HR diagram. Now coming to the HR diagram, remember, let me write it here also, sigma t to the power 4. Okay. So this is relation between L and T. Now this is the luminosity, this y axis is the luminosity, this is the temperature T, and this is the HR diagram, which tells you the position of stars with the particular luminosity and the temperature. Now suppose consider, so this part, this is the giant part, giant means stars which is in the later stage of their evolution, and it has a very large radius, and white dwarf means those stellar object which has a very lower radius than the sun. Now consider a particular temperature. Suppose we are on this line, it has a particular temperature, say 4000 degrees centigrade, just let us assume 4000 Kelvin or centigrade. Okay. So if your T is constant 4000, then that means your luminosity will depend on the r star, that is the radius of the star. And as I told you that for giant the radius is actually 10 to 100 times of the solar radius. Okay. So if the radius is 10 to 100 times of solar radius, then the luminosity will also be 10 square to 100 square times of the sun when you put this value here, right. So it is very obvious that the giants will be on the upper part, on the higher luminosity side in the HR diagram. Why? Because the main factor is the radius of the giants are very large. So and the luminosity goes as radius square, so that means the luminosity will goes as 10 square to 100 square, and the luminosity will be very much high than the sun, and the position of the sun is generally in this region. So this is the region where the sun is, and it is called the main sequence. Most of the stars are follows this main sequence, and giants are above the main sequence because of their large radii. Similarly, for white dwarf, the radius is actually few, you can say 2000 of kilometer, which is much less than the radius of the sun. That means this luminosity will be lesser than the sun. That's why you can see that if you consider the y axis only, the white dwarf is lower than the main sequence because it has lower radius and it has lower luminosity. Okay, so here I have considered a particular temperature because the temperature of the giants are not that much, and those are mainly in that region. Similarly, for the white dwarf also you can consider a particular temperature which is say 15,000 Kelvin, and for a fixed for this fixed temperature, the stellar luminosity is much higher because of their higher radius, and the white dwarf luminosity is lower. So this from this you can find two questions in our assignment, that what are the where the giants or the white dwarfs are mainly situated, or the position of the giants and the supergiants and white dwarf in the HR diagram. So remember, always remember this thing, that your luminosity is the surface area of that particular star or the stellar object times sigma t to the power 4. So if you are considering a particular t for understanding, then R high means luminosity high, R low means luminosity low. Okay, so that is the reason why giants are above the main sequence and white dwarfs are lower the main sequence. Okay. Now remember this. So one thing you can ask, that why giants have this much of radius than the sun, how they are so big, and why white dwarf are less in radius. So that I will discuss, if possible today I will discuss at the end, or in the next class I will discuss it, why giants have a higher radius than the normal star. So giants are also star. This is the late evolutionary stage of a star. So a star has a life cycle, it forms, then it burns its fuel, which is hydrogen, helium, and then it will die in the supernova phenomena. So this is the life cycle, rough life cycle of a star, and at the late stage, when it is near to its death, this red giant, these supergiants generally form. Okay. Now, okay, so this was the first two questions. Now I will go to another important thing that so if you have any question, you can ask. So I will just go through the overview just very quickly. So your first, you knew, that is the energy density per frequency range, that is coming from the pure black body assumption. Then from that we have calculated the I nu, which is the intensity of the black body radiation, and that's why the concept of steradian, that means the angle, solid angle, comes into the picture. Then from that I nu, if we integrate over that all the solid angle, we will get the flux F nu through a unit surface, and if we integrate that and if we multiply that F nu throughout the whole surface area, we will get the luminosity. Okay, and if you want to go from the frequency dependent part to the volumetric value, then you have to do another integration, which is over the frequency range. So that is the main thing, that by that procedure we have calculated the luminosity, and we have found that luminosity is related by this relation t to the power 4 and r star to the power square. And from that understanding, we have I have tried to explain why the giants and supergiants is above the main sequence and why the white dwarf is below the main sequence. It mainly depends on the radius of the stellar objects. So these are stellar. I am saying white dwarf and stars as stellar objects or stellar companion, and this main sequence is the stars, which is in the burning phase. Okay. Now going to the cosmic microwave background. So it is a very important thing, that cosmic microwave background, and interestingly you can see this also follows a perfect black body type spectra. This is also a BB type spectra, black body, which is followed by the stars also. Okay, this is a remarkable findings. So what is this CMB? Okay, so I will tell you the origin of how the CMB originates. So at the beginning of the universe, when it was just forming, universe was confined in a very small space. This was the whole universe. It was concentrated at a very small space. You can think it as a point. So the density, the temperature, everything was very high in that particular region, and that, okay, and the temperature was in billions of degree centigrade, billions of degree. Okay, so if you have some temperature associated, you will find some thermal energy, right? So kT, if your T is the temperature, K is the Boltzmann constant, then kT will tell you the thermal energy of a particle at a temperature T. So this is equivalent to the energy. Okay, so if your energy is in billion degree centigrade, your kT value, the energy, if your temperature is billion degree centigrade, your kT value, that means the thermal energy, will be very high. That means it will be so high that for a typical hydrogen atom, you know that the binding energy is 13.6 eV, right? But at billion degree centigrade, it will be much higher than the 13.6 keV EV energy. Okay, so what happens that at that hot, it is called the quark gluon plasma. At that hot temperature, no matter can be formed, because whenever a electron will try to bound with the proton and make a hydrogen atom, as the temperature is very high, it cannot be bounded. Okay, so the formation of hydrogen cannot happen at the very high temperature, and everything will be, will be in isolation. You can say there will be free protons, there will be free electrons, they cannot combine because of that high value of energy. So there will be quark, gluon, protons, neutrons, electrons, everything will be there but free, not bounded, and the density will be very high. So if there is a photon created by some phenomena, that, so suppose this is your that region, this is that region, and you have very high value of particles here, and you have photon of light that will scatter from here to there, from, it will randomly scattered within that volume because of that free particles, and it cannot come out of the, that region. So the photons are there, but they are confined within the volume because of the very high density of free atoms, and the photons is scattering at the free atom. So this region, this is not a good color. Okay, so this region here, you can see a very concentration of the free atoms, free particles, not atoms, and light cannot come out of this particular region, so light is confined. That means you cannot see anything beyond that volume, because it is very opaque, and if photon is not coming out of that particular region, you cannot get any information, because photon is the main information of the region. So for the observer, it is opaque, you cannot see anything beyond that. Now after some time, from the beginning, the universe is expanding in its size, and with expansion, the temperature of the universe is decreasing. The expanding universe, that means temperature is decreasing. But fine, so temperature is decreasing, that means kT, the thermal energy, is decreasing, and after some time, that is if I correctly remember, so 380,000 years after the formation of the universe, the temperature will be around 3000 degree. So from billions of degree, it has been fall to 3000 Kelvin. Okay, and this temperature, if you calculate at this temperature the thermal energy kT, you can find this. It is possible to create hydrogen, because the thermal energy now is lower than the 13.6 eV energy, so that the thing can be formed, and it cannot be again relaxed. It cannot be, the electron cannot be out of the orbit after formation of the hydrogen, because the thermal energy has been low. So if your kT is less than 13.6 eV, which is the energy of the hydrogen atom in the first orbit, so then hydrogen can be formed, and if your kT is greater than 13.6 eV, no bounded atom. Okay. So at 3000 degree Kelvin, this situation is happening and hydrogen is forming. So you can see in this picture also, this is showing as a time, propagation of time. So after some time, roughly it is the what I told you, it is the 380,000 year. So after that, temperature has been decreased, and the formation of hydrogen, you can see this is the protons and this is an electron. So formation of hydrogen happens, and these photons can move, can left that place, and it can propagate through the universe. So in this case, the photons are confined, it cannot come out of the volume, but in this case the photons are now free, it can move through the space because the concentration has been decreased of the free particle, and the number of scattering for the photon has also decreased. So it can go out of that particular volume, and it can move through the space freely. These photons are actually the cosmic microwave background photons. This is the CMB, which is the oldest information of the universe. No information is beyond that CMB, because it is the first light of the universe, we tell it. So this is the cosmic microwave background, and this is coming from all the region of the universe. So it is homogeneous, and if you measure the intensity of this CMB, you will find this plot. Okay. Now this plot is this has been plotted as a frequency, and this is the intensity. So as I told you, we generally measure the intensity or the flux, we cannot measure the energy density. So this has been measured, and you can see this is also following a black body type spectra, and the temperature for this curve is 2.7 Kelvin. This is important, you must remember that part only, that 2.7 Kelvin is the temperature, associated temperature, and the peak, which you can calculate from the Wien's law, that you know that lambda mt, that is the lambda max T is 0.29 semi-Kelvin, and nu max T is 2.8 kT, where K is the Boltzmann constant and T is the temperature. So if you calculate from here, these are called the Wien's law, you can see the peak sorry, it is at 160.2 gigahertz. So you can see this is 150, and it is just beyond that 150, that is gigahertz, and corresponding lambda, so this is nu max, and corresponding lambda is 1.9 millimeter. So this 1.9 millimeter belongs to the microwave background. So we have different types of electromagnetic waves. So the microwave generally, 1 millimeter to 1 meter. So this lies in this in this range, and that's why we called it cosmic microwave background. That's why the microwave name comes. Okay, so this is the main thing, cosmic microwave background, and as I told you, this CMB is coming from all over the universe. That means it is very homogeneous, and you can find that the fluctuation is generally 1 in 10 to the power 5 or 10 to the power 4 times. So this value is very less, the fluctuation is very less, and that's why we called it a homogeneous background, microwave background, cosmic microwave background. Okay. So but one thing I want to tell you, that this value 2.7 Kelvin is the value which we are measuring right now, but when these photons started to move through the space, at that time this temperature was 3000 Kelvin, as I told you, and also I told you that with expanding universe the temperature is decreasing. So this 3000 Kelvin was at 3,08,000 year, and now the age of the universe is 14 billion year. So you can see it has cooled much further from the 3000 Kelvin, and right now the temperature has come to 2.7 Kelvin. Okay. So from 3000 Kelvin we have come to 14 billion from 3,80,000 year, we have come to 14 billion year, and this 3000 Kelvin has been decreased to 2.7 Kelvin only. So, at the beginning of the CMB, the temperature was not 2.7 Kelvin, it is right now we are detecting the temperature. It can go below that also with the more age of the universe. Okay. And similarly, it was about the temperature. Similarly, the wavelength, which is 1.9 millimeter, which is in the microwave regime now, it was not in the microwave also when it started to move through the space, because at that time it was, I mean, I will tell you what is the redshift. So, it has been redshifted with time, because with the expanding universe the redshift comes into the picture, and redshift tells you that the wavelength will increase with time, okay, or with distance, whatever you can say. So, that is why the wavelength right now we are detecting in the microwave range. Before it was not, it may be not in the microwave range, and it was in some other range. So, that is the point you have to remember, that this CMB was always not microwave background, it was some other wavelength also, and the temperature was was very high at the time of beginning. But right now just focus, the temperature is 2.7 Kelvin and the wavelength is 1.9 millimeter. You can also remember the, I mean, frequency of that CMB also. So, this is the important part, and that is why it is microwave background. Okay. Okay. Now, any questions? Sorry. Let me check. Yeah. So, you will find another question. I will not go through the question one by one, because those are very easy, and I have seen that the other TA Nilakshi has already done that. So, the temperature of the CMB, that was a general question, and you will mark 2.7 Kelvin. Okay. And okay, so that is good. Now we will do, what is happening? Yeah, redshift, what I told you actually. So, there was a question about redshift, that is why I took this topic. Okay. So, I think everyone who have done the basic BSc course knows about the Doppler shift of the wave, I mean the sound, more precisely Doppler shift of the sound. So, when a source of the sound is coming towards you, the frequency will increase, and when the source is going far from you, the frequency of the sound wave generally decrease. So, this is the observer, and it is the source. So, for our case, the source is the sun, and as this Doppler shift is the nature of the wave, light is also an electromagnetic wave. So, what happens to the sound, it will happen to the light also. Okay. So, for our case, the source is the sun or star, any star, not sun. So, if the star is going away from you, then the frequency decrease. Frequency means nu decreases, and nu decreases means lambda increases. Okay, because nu and lambda inversely related. C equals to nu lambda. Okay, so nu proportional to 1 by lambda. And similarly, if the source of the light or the electromagnetic wave comes towards you, then the nu frequency increases, that means lambda decreases. Okay, so this is the classical case of redshift and blueshift. So, this is called lambda is increasing, and lambda increasing means the wavelength is increasing, and the maximum wavelength of light of the optical spectrum, which we can see, is red. That is why we call it redshift, because it is shifting towards higher wavelength side or the red light side. And if and the blue has the lowest value of wavelength, that is why we called it blue shift. So, okay. So, redshift and blueshift are very important. Remember always, whenever a object is going at a farthest distance from you, it will show the redshift, and when it is coming towards you, it will show the blueshift effect. Okay. So, this is actually the difference, which is the original, because this source is emitting at a original. Original means I will denoted as lambda source. So, lambda source is the original wavelength which is the source emitting, and we are observing the lambda which is different, which may increase or which may decrease depending on the red shift or blue shift, that is lambda observation. Okay. So, that lambda for the red shift case, lambda source is less than the lambda observed, as I told you that we will detect a larger wavelength. So, the delta lambda, which is the difference, that is lambda observation minus lambda source observed by lambda, that is delta lambda, and z, which is the red shift, that is denoted by delta lambda by lambda. It is nothing but lambda observed by minus lambda source by lambda source. Okay. So, this is the main thing for the electromagnetic case. Now, I was telling about the classical thing. Now, as you know that light generally travels with the velocity c. That is why we need a relativistic correction for the Doppler shift or red shift for the light, and that is why this expression comes into the picture. I will not derive it, just remember that whenever you can see a v by c term, always remember that this is coming due to relativistic effect. So, this z is equals to 1 plus v by c by 1 minus v by c under root of the whole thing and minus 1. Okay. And if your v is very less than c, then you can say here this v. Okay. So, this v means the velocity, the velocity of the source, and this c is the velocity of light. These are different, right? Because the source is not moving with c velocity, it is moving with v velocity, which is very less than the c, because it is an extended source. But the light which it is emitting, it is moving with the c velocity. So, that is why the v and c are different, and if your v is less than c, as I very less than c, as I told you, an extended object cannot move with the speed of light, it moves with a very less velocity, then approximate result will give you this type of expression, that z is equals to v by c. It is just the approximation of this particular expression. So, you can, I mean, binomial, you can do the binomial expansion if v by c is very less than 1, and the same thing has been done here. So, z equals to v by c, that means v, the velocity of the object, is equal to z by c, right, and you can calculate the z by observation, the redshift itself. So, you have the value of v here, right. Very good. So, by observing the redshift only, we can calculate what is the velocity of that object. So, I have shown also in the picture here. So, here you can see that it is at rest. At rest, the spectrum looks like this, where these blacks are particular lines, and if it moving towards you, that means blue shifted, and I told you that blue shifted means lambda will decrease for blue. So, you can see here the lambda has been decreased. So, this has gone to, I mean, this should have come like this, but the shifting is towards the lower wavelength. So, this is the increasing wavelength on the x axis, and for the red shift, lambda is increasing. So, you can see also here it should be here for the rest case, but the shifting is towards this direction. This is now the position. So, lambda is increasing. This is the image I found in the internet, that is why I show you, and this figure is also showing you the dependency of distance. So, this was the rest frame spectra of a particular source. Now, if it is nearby, that means the distance is not okay. So, I will come into this picture after doing this. Okay. So, as I told you that if you know the redshift, you can calculate the velocity. Now, in our question, it was given another information, that is depends on the Hubble's law. So, by combining this redshift theory with the Hubble's law, we have to calculate the distance of the object. That is very important. So Hubble's law says that V is equals to H0D. So this particular expression I cannot derive you, or I cannot tell you how it is coming, because for that you have to know a little bit of cosmology, which cannot be completed here. So just remember that, just try to remember it, that V is equal to H0D, where H0 is the Hubble constant and D is the distance to the galaxy. Okay, so from the redshift thing you have calculated V equals to ZC. From the Hubble constant you have V equals to H0D. Now you can compare these two. That means ZC is equals to H0D. That means the distance is ZC by H0, right? So your H0 is known. This value has given is fixed value. This C is also known, the velocity of light, and this Z you can calculate from the given redshift. So the all the values of the right hand side you have in your hand by calculation, and by putting that value you can just calculate the distance, what is the distance of the source which is emitting that light, which has been redshifted to a particular wavelength. So this is the this was the statement of the problem. I will not go through the line by line calculation. Just do this, that you have to equate the velocity of the object from the both theory, that means from the redshift and from the Hubble law, and you can calculate the distance. Okay. This is the main part. This ZC equals to H0D. Now, so by in the calculation there is nothing, all the values are given, just put it and you will get the result. But just pay attention when you are putting those values. Put everything in CGS or put everything or SI, whatever convention you use, just follow that particular thing, otherwise you will get a absurd result. Okay. Now while I was going through that question, I found that here there it was given that H0, the Hubble constant, in some megaparsec unit or parsec unit, I cannot remember clearly, but I thought that it is important to understand what a parsec means. I mean, you have measured the distance in kilometer, centimeter, meter, but you have not used the parsec. In astronomy we generally use the parsec unit for our distance measurement, and I will give you a brief idea of that parsec only. Okay. Oh, okay. So as I was telling another thing, like this figure, so you have ZC equals to H0D, that means Z is equals to H0D by C. Okay. So I am just trying to explain this figure. So if your D, so Z is linearly depending on the D. If your D is higher, that means your redshift is higher. Okay. So Z proportional to D, because H0 and C are constants. That is exactly shown in this figure. So it is the basic spectra, I mean rest frame spectra. If your D is a nearby galaxy, I mean D value is low, I mean small value, the shift is very less. You can see that this blue line has been shifted to this blue line and the shifting is very less. Now if you go to a distance galaxy, your D is increasing. Okay. So your D is increasing in this direction, the y axis. Then this line has been come to this particular line, and now the shifting is a very large, because your D is increasing. If you further increase your D, that line is coming to this part. So you can now see this was your rest wavelength, and this is your now the observed wavelength. It is a big separation. So from the separation of the line you can get also an idea about the distance, whether it is coming from a very far away object or it is coming from a nearby object, because redshift is proportional to the distance of the object, just this. So that's why I kept this figure. Okay, now I will come to the part, what is a parsec. I will try to give you an idea and how this distance measured. We cannot, I mean we are measuring a distance which we can never reach. How we can do it? So this is called a parallax thing. I am erasing this part. So this image is showing you the parallax. Parallax is a method to measure the distance of the object. I will tell you. Okay. So suppose this is the sun. Okay, so in so this is the sun. In astronomy, this denotes the sun, and this is the earth. So it is rotating around the earth. Earth is rotating around the sun. Okay, very good. Now let me put it here. Yeah, this is the earth. Now suppose you have a star here and you want to measure the distance of the star. So by doing this, I will tell you how the parsec comes into the astronomy. Okay, let me draw it in a straight line. Yeah. Okay, so the observer which is sitting at the earth, he can see the, I mean, for him the distance is like this. So this is the distance. Let me call it at L. Okay, now after 6 months, the earth will come here in its orbit, because it is the 6 month after 6 month gap. Ideally I am making it in a straight line so that you can easily understand it. And for this position of the earth, the observer will see the star like this. Okay, now you are measuring just one star, you have more stars in the farthest distance. So the observer will see a background where there are numerous number of stars, other things, whatever that can be. Okay, so there can be numerous number of stars. Now suppose, okay, so when the observer is looking from position A, it will see the star in the background of this particular star. Okay, suppose this is a star A. Yeah, star A. From position A, this is our measurable. I mean, this is the star which we want to measure the distance. Okay, this is our object, and this is the background object. This all thing is the background of the star. Now, and from the position B, it will see this object which we want to measure in front of this particular star B. Okay, now there are some techniques by which we can measure the angular separation of the star A and star B. I mean these two. If these two stars are known to you, you cannot do it for a random star, because the distance of all the stars we don't know. But suppose luckily you know the background star A and star B, and you know the separation between it. So let the separation be theta, and from the geometry you can see this angle is also theta, right? So, and okay, so this line, this whatever, this is a D. This D will roughly, I am saying it roughly because it is very large distance, so roughly you can say that it will divide the angle by theta by 2 and theta by 2, and I am telling that as alpha. Say alpha. So alpha is the theta by 2. Now consider this particular triangle. This is a right angle triangle. It is a 90 degree. That is the alpha. So and this distance is 1 AU distance, because you know the distance between earth and sun is 1 AU, the astronomical unit. So this 1 AU you know. Now if you use tan alpha, so tan alpha will be D by 1 AU, right? Tan alpha will be D for the right angle triangle. And this is very large distances, so alpha will be very small. Alpha is very small angle. I mean, it is not even in degree. I mean, degree is a very large. You can think it as of second, arc second. Okay, so alpha is very small, and if alpha is very small, we can write tan alpha is nearly alpha, that we have done in mathematics. So alpha is equals to D by 1 U. Now you have the alpha, you can you have this measured value, and you know that 1 AU. So from this you can measure the D, which is the distance of the star from the sun. or from the earth, because this is very large and I have not shown that in the figure. So, the distance from the sun is roughly equal to the distance from the earth. So, this is the main distance, I mean, of the parallax. This is called the parallax, and this alpha is called the parallax, and the theta is called the parallax angle. Okay. So, that is how we measure the angle. Now, that is how we measure the distance. So, it is valid for only few parsec or few kiloparsec stars, not beyond that, because in that case the theta will be very less and you cannot measure with the instrument available on the earth. So, other indirect methods are used. Now, so alpha was d by 1 AU. Okay. Now, parsec is defined in such a way that if your alpha is in 1 arc second, that means it is 1 by 3600 degree. You know that 1 degree has 60 minutes, and 60 minutes has, and each minute has 60 arc second. That means 1 degree has 3600 arc second. So, if your value of alpha is 1 arc second, that means this value of alpha is 1 arc second, then the distance which we can calculate from this parallax method is called that 1 parsec distance. So, if your d is 1 parsec, it will create an 1 arc second parallax angle. Okay. So, that distance which creates a parallax angle of 1 arc second is called the parsec unit. That is per second, that type of thing. So, and the value of 1 parsec is 3 into 10 to the power 16 meter, I think. Just check it. I have it. Let me see. Okay, just check it. It might be right, the 10 to the power 16 meter. So, whatever, you can see that value is very high. Okay, and it is 3 into 10 to the power 18 centimeters. So, it is difficult to write every time that 3 into 10 to the power 16 meter or 10 to the power 18 centimeter. It is a more easier way to use that parsec unit as the standard unit of general distance of the astrophysics. So, that is what the parsec is, and for this mathematics you can see that the Hubble constant is given in megaparsec. So, megaparsec is nothing but 10 to the power 6 parsec. I have given you the idea of parsec, and you can extend it to megaparsec, gigaparsec, whatever you want. Okay. So, that exactly what I tried to draw there has been shown in this figure. So, this is, yeah. Do you have any questions? Okay, then I mean, you can mute and go continue the class. Good evening. Yeah. Okay. So, yes. Oh, I am Saurabh Bhadra. Okay. So, for this course there are 2 TA has been assigned. One is Nilakshi from IIT Kanpur, and I am from IISc Bangalore. Okay. So, generally this class will be in Tuesday 6 to 8 p.m. but there was some problem in this week. That's why only for this week I am taking it on Saturday. Otherwise, from the next class it will be on Tuesday 6 to 8 p.m. Okay. So, I was telling about this picture. So, you can see this is the earth position. This is in a line, the earth, sun and the earth. So, December and June, that is the 6-month gap. Any 6 months gap you can take, so that it is in a line, and this theta is the parallax angle which has been measured along this background. Okay. This is theta. So, similarly, so according this picture, this is 2 theta. This is 2 theta and this is theta, what I have written as alpha. So, this is the parallax method actually. Okay. Now, you have some idea about how the parsec length is coming into the picture of the astronomy mainly. Okay. Okay. Now, so you can go through that math, I mean that problem which has been given. Now, I will come to a, I mean not important in nuclear astrophysics, but I think you will find it interesting. Where is that? 1 4 3 I have written. Where do I have- yeah, this is okay. So as you know, sir told you in the first few lectures that generally star formation happens in nebula. You have come across this line that nebula is a cloud of gas, you can say, and if gravitational collapse happens, then there will be stars. Now very briefly I will, it is not related to the assignment, but I think it is of great importance and you can find it interesting. So how this star formation happens with the very simplest mathematics. Okay, so that I want to do here. If you don't want to go through this, it is okay, no problem, but it is interesting, you can see. So this image is actually a simplest representation of the nebula, that big sphere which is a collection of gas, and star formation will happen inside that nebula. Okay, so here I have written, one of the classic problems of astronomy is the modeling of the gravitational contraction. This is the main reason of the formation of stars from a nebula of a diffuse cloud, that is nebulae for plural, of gas and dust to form a star. So we will try to find out how it happened. Okay, so let us consider a particle, a particle or object of mass m at the distance of r from that nebula, center from of the nebula, and the mass of the nebula is 4/3 pi r cube rho 0. Rho 0 is the density of the nebula. Now that typical Gauss law that tells you that it will, that particle m, this particle will feel the gravitational attraction of the whole system, as the whole system is concentrated at the center of that particular sphere. Okay, so this is the typical Gauss law, which tells that Fg, which is the gravitational force that the mass of m, small m, feel, that is g mm by r square. This considers that the total m of the total m mass of the nebula is concentrated at the center of nebula. Okay, so this is the gravitational acceleration, gravitational force which is acting inward on that mass m, and so it will feel acceleration towards the center of the gas, and we will just use the conservation of energy only, nothing but that conservation of energy. It is a very simplest picture. Generally it doesn't happen because there are many other effects like turbulence, pressure, everything, but it is simplest idea how it can form. So okay, so let us consider this mass under the effect of the force of the gravitational, gravitational force. It is moving towards the center and it is reaching to a distance r, and the initial distance was r0. That means I am taking that this distance is r0, and after after some time it has come to the distance r. So the energy change, that the potential energy change is this, and this must be converted into the kinetic energy of that mass. This is nothing but the conservation of energy, half mv square. The kinetic energy is equals to change in the potential energy from coming from r0 distance to a distance r. Okay, so and so v square is equals to, you can see there is no effect of the small m here, only the capital M, the mass of the nebula is important. So 1 by r minus r0. Now if you substitute the m as 4/3 pi r cube rho 0, so 2g 4/3 pi r0 cube rho. Why I put r0 instead of r? Because I am considering the initial distance of the mass was r0. So it will follow, so it will feel the effect of the mass, which is r0 cube of rho 0. So you can see this r is actually r0, no problem in that. Okay. So this if you calculate, I mean, I will not do the steps, so you can follow this. R0 square rho 0, it will be r0 by r minus 1. Very good, this one. Now nothing, you just do the integration. I mean, you just write it in this way, 8 by g rho 0 r square root over r0 by r minus 1 half. Okay, half, and this is v, that means dr dt. Just do the integration, that dt is, let us write it as capital A, I am not writing it again. So r0 by r minus 1 to the power half dr. Okay, and we are considering that the particle is coming from r0 distance to r distance at a time 0 to t. Okay, so that will give you t equals to, yes, what background means, I mean the background of this particular problem. Can you say in details, like which one? Yes. No. Okay, not going to, so it may be confusing. So r0 is this distance, the initial distance of the m, that was the r0, and from r0, say it is coming to this distance. Now after some time t, the mass has come to this point, and this distance is, so let me do it on the line. So after some times it comes to this point, and this distance is r. Understand? So this was the thing, the mass was here at the time 0. So got it? It was r equals to r0 after some times. So t, say t dash, it is r equals to r. Okay. Okay. So if you do this integration, you will get the t, and this is called the free fall time, TFF, 3 pi by 32 g, and this is a very important parameter for the astrophysics. If you, if possible, try to remember that this relation, that 3 pi and 32 are constant, but it is proportional to g rho 0. Rho 0 is the density of the mother cloud you can say, for the stars, and g is the gravitational constant. It is very important, I mean very much important, this relation. Okay, so you can see that after TFF, the particle will come towards a distance. Similarly, a particle from here, it will also feel the gravitational acceleration and gravitational force, and it will go inside, and particles from everywhere, it will go towards the center of that nebula, and after some time, so all the particles will be around that center. You can see this is the main basic idea of the star formation, because as the particles has gone to a very smaller distance now from a bigger distance, that means the concentration of particle, the density of the region has become high, and this eventually results in the formation of stars. So by using that only the simplest conservation of energy, you can just get an idea about how the star formation happens in the nebula. That I wanted to show you, and an interesting result that so suppose, so it was the formation of star from the nebula, right? And the similar thing can happen for a star which has already formed, because for a star it is a circular thing and it has the gravitational force, and but you can ask those how the stars survives. So those survives because, so for stars the similar thing happens, it is a star not a nebula, suppose it is a mass, it is feeling that gravitational force inward, but on the same time it will feel and pressure force outward because of the nuclear reaction inside the stars. So up to which time Fg and Fp, I mean this is in equilibrium, the star will be in its shape, and when your nuclear burning is ending, coming to an end, your Fp will be not there and the Fg will dominate, so the star will collapse. This is the reason of supernova also. So always for a spherical star like body, it is the equilibrium between the gravitational force and the pressure force, but this pressure is coming from the thermonuclear reaction. But for the nebula, it is a very low dense thing and there is no thermonuclear reaction to hold that gravitational force. That's why it is coming towards the center. That is the main difference between the star formation and the formed star, already formed star. Okay, but one interesting thing you can calculate, suppose your nuclear reaction is ended in the sun, your Fp is not there, so it is just acting like the nebula, that it the star is contracting, there is no outward force. So the free fall time scale will be same like TFF 3 pi by 3200, and if you put the values like m is 2 into 10 to the power 30 kg for sun, I have given the sun sign, and r is 7 into 10 to the power 8 meter. So if you use this parameter, you can see that for sun, that free fall time is only 30 minutes. I mean, can you imagine if there if there is no nuclear reaction inside the star, it will take only 30 minutes to destroy the star. That is an amazing result. Eventually this will also come, that nuclear fuel will be ended and that sun will be destroyed. So this is important thing, that if there is nothing inside the star, it will inside the sun, it will only stay on for 30 minutes. So it is the main, so that's why I tried to tell you that very basic idea about the star formation and collapse of a star. Star formation means also a collapse of a nebula. That is the difference. The physics is same behind all these two phenomena. Okay. Okay. Now I will go to another part. So if anyone have any question in this up to this, you can ask anytime, no problem. And if you want to send any question, you can send it to this email ID also. It is Sourav, SOURAV, Bhadra, BHDRA @iisc.ac.in. You can send any questions. Or if you want to, I mean, learn any topic before the scheduled session, you can also tell me, that I will try to cover. Okay, now coming to the course of the nuclear astrophysics. So our course mainly focus on the nuclear reaction inside the stars and the nuclear abundance, I mean elemental abundances, all those things. So the main source of the energy, so you can see at the first, I mean in the first slide, I have calculated the luminosity. So you can ask, what is the source of this luminosity? I mean, what is the source of this energy? You are calculating luminosity, everything, but you have not you have not tell us what is the source of this luminosity. So that I will tell you now, that the source of this luminosity is mainly the nuclear reaction inside the stars. So when a nuclear reaction happens, it will release some energy, and that energy will come out of the sun or the star. That is the luminosity of the star actually. Okay. So and as I will just emphasize some point which is made by our instructors, sir, that although the nuclear reactions are the main source of the stars, but this nuclear reaction, I mean, classically cannot happen inside a star. Okay. So but it still happens. Why, I will tell you. by small, very, I mean, few mathematical lines. Okay. Okay. So, nuclear reaction, we are considering the nuclear fusion, not fission. Fusion means two small, I mean, lower mass nuclei will create a larger nuclei. So, if it is M1, M2, it will become M1 plus M2. Okay. Roughly I am saying that. So, this is the fusion. Now, okay, let us calculate the probability of nuclear fusion of proton and creating a helium. Okay. So, proton plus proton is will give you helium. How this happens? Okay. Now, suppose this is the proton, this is another proton inside the star, and it is at a distance at d. Okay. So, this one has Z1 E energy, Z2 E energy. Okay. Now, for proton Z1 and Z2 is 1, you know, but I am writing in a way of I mean generalization. Okay. If instead of proton there is other element, you can just substitute the Z number according to that element. So, for our case proton is Z1, Z2 is 1, no problem. Okay. Now, okay, so these two proton, those are positively charged proton at a distance d, it will feel the Coulomb repulsion. Maybe I am writing the Coulomb wrong, repulsion. So, that is Z1 Z2 square by d. This is the, I mean, repulsive force. Okay. Now, but the reaction will only happen if there is some force which overcome this Coulomb repulsion and these two particles come very closer like this, then the reaction will happen. Okay. So, we will calculate how much energy we require to get these two particles very closely so that the reaction happens. So, actually this, when the distance, I mean this distance r is about 1.44, remember, if possible remember, otherwise you do not need. Okay. So, if the distance is 1.44 times 10 to the power minus 13, okay, centimeter, and A is the atomic number, then this reaction will happen. This is theoretically value, and at this distance the energy will be Z1 Z2 e square by r, right, where that r is 1.44 into 10 to the power minus 13 a 1/3 semi. Okay. So, if you calculate this, it will give you roughly 1 MeV energy. So, you need at least 1 MeV energy to get those protons so close that they will take part in the fusion reaction and the helium and the creation of helium happens. Okay. Now, this 1 MeV energy is required, right, but at the sun, we are considering the sun, the temperature of the sun temperature at core is roughly 1.5 times 10 to the power 7 K. Okay. And I told you at first that if there is a temperature, then there will be thermal energy associated with the temperature, that is Kt, kBt, the Boltzmann constant Kb, and T is the temperature, and if you calculate you will get that value as 10 to the power minus 3 MeV. I mean, just put the Boltzmann constant value as just T is 1.5 times 10 to the power 7 Kelvin. So, that will give you 10 to the power minus 3 MeV. So, one important trick here, is it possible? Let me check. 10 to the power 7 K. No. Okay, I will tell you that later. So, if you put these values, it will be 10 to the power minus 3 MeV. Now, you can see this 10 to the power MeV is very, very less than this 1 MeV. So, that at the core of the sun, the thermal energy is not sufficient so that the two protons come closer and take part in the fusion reaction. Still the reaction happens. Okay. So that is called, that cannot be explained by the classical part, that is coming from the quantum thing, and it is called the quantum tunneling. Okay, so this is the image of quantum tunneling. I don't know whether you know quantum tunneling or not, but in BSc I think someone, I mean, who have done the BSc, they know that there is a non-zero probability. I mean, this wave function is a proton's wave function, and this V, which is shown by this potential, is actually this value, this 1 MeV, this 1 MeV, and your wave function which has a value 10 to the power minus 3 MeV, this one. So you can see, although your particle has less value than the potential barrier, which is the required energy for the fusion to happen, still a non-zero probability of fusion can take place. So some probability of is there that the particle can cross that potential barrier of 1 MeV and come closer to that other proton, and it will take part in the fusion, and the fusion reaction will happen. So this is the quantum tunneling effect, although classically not possible. Classically not possible, because 10 to the power 3 MeV is very less than 1 MeV, which is required. But quantum mechanically it is possible through the tunneling. So this sir has also emphasized this point. I just tried to give you an idea by calculating the value, how it is, how much the available energy is less than the required energy. Okay, through tunneling. Okay, now this is the reason why the fusion takes place, that is due to the quantum thing. And you know that if 4 protons will make 1 helium, yes, so for example, a helium nucleus differs in mass from the sum of 4 protons by an amount of this. So this is the mass of the helium, and this is the mass of the 4 protons which will create the helium, and you can see there is a difference. That is the main essence of the nuclear reaction. This mass defect, or this is the difference in the mass, delta m, that will release energy delta m c square. So delta m is 4.7 times 10 to the power minus 26 gram, and if you multiply it with the c square, it will give you 27 MeV energy. So that means 4 proton has been. So I will tell you how the steps of proton to helium in the next class. Today I will not tell that. So 4 protons will come closer, and that will make a helium atom, and in that case that 27 MeV energy will be released. That 27 MeV is the source of the energy of the sun, of the star. So that's why the nuclear energy is coming to be. So here you can calculate that how much the delta m. So this is the delta m calculated by this expression. So for any element you can calculate. A is the mass number, that means proton plus neutrons. Z is the proton number, Mn is the mass of neutron, Mp is the mass of protons, and M nucleus is the mass of nucleus after forming. Mass of nucleus. Okay, so always there will be some difference between the actual nuclear mass and the mass of the constituent particle which has made that nucleus. That is the binding energy. So that binding energy is delta mc square, which will release in the fusion, and it is the reason of the thermal nuclear energy of a star. Okay, so and okay, now as I here calculated the free fall time of a sun, how much time the sun will survive when the nuclear reaction ends. Now we will calculate another this type of small thing. So okay, so as I told that your L, which is the luminosity is due to the nuclear energy released in the fusion. Okay, now we will calculate how much time is there for the sun to burn all of its fuel. That means we will consider only hydrogen and helium. All the hydrogen will be fused to helium, and we will calculate the time scale. What will be the time? This is very small thing, but very interesting. So that we will call as T of nuclear burning time. Okay, that will have that is okay. So first I will tell you some thing. So suppose this is the star sun. It has mass m, and 70% of m is hydrogen. Okay, and so first we have to calculate how much hydrogen is there. So 0.7, that corresponds to 0.7 times mass, okay, of the sun, that is the hydrogen. And of this 70%, we consider that 10% is in the core, and other 60% is at the envelope. I mean, if you divide the star by core and envelope, so the envelope has 60% and the core has 10%, some value I am taking. So it will be multiplied by 0.1, because 10% of this total mass is in the core, and that core is burning. We are considering the burning at the core only. Okay, and so if we put m in gram, then each gram, I mean, so this is the total mass in gram of hydrogen available at the core for burning, and 1 gram of hydrogen will release an energy of 6 into 10 to the power 18 arc per gram. This value is exactly coming by calculating this thing, just this thing. You calculate it for one particular element, then you can convert it for 1 gram or 1 kg. Okay, so this is the energy generation, total energy generation, right? I mean, you have this much of hydrogen, and each hydrogen is giving you this, each gram of hydrogen is giving you this much energy. So this is your total energy which is available for the nuclear reaction. And I told you that L is the luminosity that is coming out of the sun due to this nuclear energy. So it will be divided by the L, because this will give you the time scale. So L has roughly 3.8 into 10 to the power 26 arc per times 10 to the power 7 arc per second for sun. So this is the solar luminosity. Okay, so that means earth is sun is radiating energy at this rate. So you can see that this particular thing, this 3 term, has a unit of gram. This gram will be cancelled by this gram, and this arc will be cancelled by this arc, and the total unit of this tau nucleus is second. So we are correct in our calculation that we are getting our value in second or in time scale. So now if you calculate, you will find that it is 7 into 10 to the power 9 year. Okay, so that means the sun will live for another 7 billion year at least for these values. So it has this much time for its nuclear energy to give support of the gravitation, and it will not collapse. So this is a very small calculation. What I have done, I have just assumed that 70% of the total mass is of sun is in hydrogen, and 10% of that hydrogen is in the core, which is burning to helium, that means fusion. And just I have calculated, so how much energy is available at the core and what is the luminosity, that means energy radiation rate. So the total energy by energy radiation rate, that will give you the time scale, up to how much time this energy rate will sustain. So that is 7 into 10 to the power 9 here. Okay, this is another important thing. So this will not, I mean, this is, there is nothing related to this in your assignment, but because all the other assignments are straightforward from the class, that which has the I mean stone that chrome. I also forgot that you can find that name and the elemental abundance. So that's why I am not going into those part, but I will tell something about the elemental abundance because it is our important thing. So I think I suppose you have assumed this part. You have understand this up to this part, how the nuclear reaction happens in the inside the star using the quantum mechanical phenomena, that is the tunneling and the available energy in sun. Okay, okay. So now we are coming to the last topic of today. Okay, so that is the abundance, elemental abundance. So elemental abundance means uh, the element, I mean the element which is in the universe. So it is not fully hydrogen or not fully helium, there are all the elements. Okay, so but there is another point, the abundance is not homogeneous also, because you can see there are various types of object in the universe. There are stars, there is ISM, that is the interstellar medium, which is the medium between two stars. There are cosmic rays also. All the abundances of these particular different things are different, they are not equal. Now generally we refer by cosmic abundance is the abundance of the ISM, not particular object, the interstellar medium, I mean the surroundings of that object. What is the abundance of that? So that is called the cosmic abundance. For star it will call the stellar abundance, for cosmic ray it is cosmic ray abundance. So like that. Now this is the thing, this is the elemental abundance plot, and you can see hydrogen and helium has a very high value. So these hydrogen and helium are actually coming from the era of the Big Bang or nucleosynthesis. As I told you in the CMB case, that after the Big Bang, after 3,80,000 years, the formation of hydrogen started, and after some time the formation of helium also started. So this hydrogen and helium are the actually those primordial part which is happening at the Big Bang. But those are the main contributions, that's why it is very high relative to the other particles, because hydrogen and helium has been created at that time in a large quantity. Okay, now all the other elements that are coming into the ISM, that the interstellar medium. So ISM is interstellar medium. Okay, so like I told you that the life cycle of a star forms, then it burns its energy, and at the end it will it will results in the supernova, that is the blast of the star, you can say, by that is the death of a star. So in that burning process, that is called the nuclear burning process, so this there will be several type, I mean structure. So this structure you can see, this is the structure which showing you the burning of the nuclear fuel inside the star. Okay, so the burning will start like this. So this is the sun, this is the star, this is the core. The temperature of the core is very high, I mean most highest temperature will be at the core, and the fusion will start from the core. This core will fuse hydrogen to helium, then helium to other elements, then it will go to upper elements. Upper elements means upper higher atomic number or higher proton number elements, I am saying, and it will go up to iron. And iron is the stable element because it has the highest binding energy. So at first this core will be iron core. Okay, so in this figure you can see this core which is written here is iron core. Iron core has been, I mean there, iron core is there. So when iron core is there, just try to understand step by step. So iron core formed, iron core, that means the core has no the burning at the in the core has ended. Okay, and as I told you, when a burning will, I mean there is no burning, there will be no outward pressure, so the gravitational pressure will try to collapse the core. So it will try to collapse this core only, not the whole star. So that core will try to collapse, and as it collapses it will release gravitational energy, right, because Gm 1 by r minus 1 by r0, that is the gravitational energy it will release. So it will release the gravitational energy, and that will heat up the outer part, the envelope. So it is the envelope, it is called the envelope or the outer part of the core. So it will it have heated the released energy due to the gravitational construction as heat up the envelope. So now that envelope has sufficient energy so that it can start the fusion. So from hydrogen to helium fusion will start at this envelope. Okay, at this envelope. Pardon my drawing, it is not that good. So in this region, in this core, in this envelope, the hydrogen to helium burning started. So so helium burning at envelope. So you can see that the core has been formed as the iron core, but the helium burning has started at the envelope. This procedure continues, and this type of formation, I mean occurs where you can see that the center will be iron core and the envelope has silicon. I mean it has been not it has still not gone to the iron, because before iron there will be silicon. When you are going outward from the center, the nuclear which is existing at that particular time will be lower and lower. That means you can see that outer envelope is still burning hydrogen because it has not gone to higher metal, but here this is carbon. That means I want to say that if you divide it like so, it has created iron, it has created silicon, it is carbon, it is hydrogen. So you can see whenever you are going from center towards the envelope, the mass center have Fe, iron, higher mass element, then silicon, then carbon, then hydrogen from center to envelope. Okay. So this type of, this is called the cell structure of the star. This type of structure forms where different regions are burning different type of elements. Okay. Meanwhile there will be oxygen also, helium also. So just the penultimate shell, which is just the inner shell of the last outer shell, that is helium, and the outer shell is hydrogen. So this is the pre-phase of a supernova. After some time the star will explode and it will create the supernova. How the supernova will happen today I will not tell you. If you are interested, I can tell you in later classes. When the star is exploding, all this metal which has been created at these different cells, that will be deposited in the ISM, that interstellar medium. Okay, sorry, interstellar medium. So that is the one of the main source of higher elements in the interstellar medium, that is coming from the supernova explosion. But the elements has been created within the star. Now it has been deposited in the ISM due to the supernova. That's why you can see this iron has a high peak, this silicon, carbon, oxygen, all these elements has been created in this cell structure, and now it has been deposited in the ISM. So that's why the elemental abundance of these elements are quite high. You can see and you can relate it with the figure which I have shown you. Similarly, there will be nickel, other elements also will be there, but the main reason, one of the main reason is this, that the supernova explosion. And but you can see here, you cannot see any lithium, beryllium or boron in this particular structure. Okay, because those will not be created, though only those particles will be created in the fusion which are more stable. But still there is some abundance, although it is low, of lithium, beryllium and boron, and this is coming from the cosmic ray spallation. It has also been discussed in the class, but I wanted to relate it with the different phenomena. So this hydrogen and helium are coming from the primordial nucleosynthesis that we will study in due course, and all these higher elements, metal type elements, are coming from the nuclear burning at the star and deposited in the ISM through the supernova. And this lithium, beryllium, boron is coming from the cosmic ray spallation. Now what is cosmic ray spallation? So actually cosmic rays are very high energy particles, so I know much about cosmic rays because I work mainly on cosmic rays. So cosmic rays are very high energy particles. So when they propagate through the ISM, like ISM means, I mean, here it is a star, star, star. So this region, so if I, so this region is called the ISM, which is the interstellar medium. Interstellar, that means intermediate medium of the stellars, that is interstellar medium. So when a cosmic ray will propagate, so cosmic rays are very high energetic particles, it will propagate through the ISM, it will propagate, and while propagation it will interact with the elements which are existing in the ISM. These are also ISM elements, right? ISM particles. This may be iron, proton, helium, whatever that may be. And these cosmic rays are different from these ISM particles because these cosmic rays are coming from other sources. I will not discuss what are the sources here because that is not important. But think it as like so think it like that, this. So there is a river and the fish is swimming through the river. So the fish are the cosmic rays and the river has water particles, water molecules or whatever. So that particles are ISM particles. So that will interact with the ISM particles and that will go through the spallation. So this 6C12, it is the ISM particles, okay, ISM particle, and this 1H1 is the cosmic ray particles. It is proton, just cosmic ray particle. So if this interact, this is also a type of nuclear reaction, then you can see boron can be formed, beryllium can be formed, and similarly in few reaction there are lithiums can also be formed. So this is actually called the spallation, and the lithium, beryllium and boron, the main source of those elements are this cosmic ray spallation. Okay, so that's what the importance is. Then all the other elements are quite low, and this can be formed in various nuclear reactions also, but our main important part is up to this nickel, iron or nickel, whatever you say. This is the most elemental, most abundant element, and we are trying to understand the source of these elements differently, and in due course we will go through nucleosynthesis and all the other things in details. So this was the main thing. So you can see that there are some questions that how lithium, beryllium and boron are formed in your assignments, and that how, what is the elemental abundance. So elemental abundance value, that exact value I have not put it in my slide because in search lecture that is there, you can refer to that, and that was the direct question, so no problem. So this is what I wanted to say for the first day. Now if you have any question or if you have any I mean idea to share, you can tell me. Okay, so for today it is end. Sorry, hello. Assignment, I have discussed the problem related to the assignments only, but the I mean I have, if you go through the whole video you can solve the assignments. I will not go through each and every calculation because already that other TA Nilakshi has done that in detail. So I thought that will be a waste of time, so I tried to give you some basic ideas about the questions of behind the questions of those assignments. But if you follow this, you will also be able to do the assignment. Now tell me if you whether you want to me to solve the assignment. That also I can do from the next class. How you want this class to be done, whatever, I have no problem, but those assignments are very easy, no problem. Sorry, I cannot. Yes, I cannot hear you. Sorry, last exam means? I don't remember the exact date, but I don't remember the exact date, but it is in some last of April, I think, right? So I will tell you in the next class what is the exact date. I have the exact date also, but I forgot right now. It is in the last week, that much I remember. Last week or the third week of the April. Okay. Okay, so then thank you for joining today, and remember from the next week the classes will be in Tuesday 6 to 8 p.m. That is the regular timing of this particular class. Okay, so we will meet this Tuesday at that time. Okay. So, and if you have any question, you can mail me also. Let me show my mail ID again. So this is my mail ID. Okay. Okay. So thank you. Let's end today here.